So we're continuing our conversation here about sets, and what we have on the screen is something you've probably seen before, is a Venn diagram. And so notice here that we have two sets. We have a set S and a set T. And notice that there's some overlapping here. So these are elements here that are in both sets. And this should be then the set of all the elements that we're talking about. And then so they're saying that this is an image of the union of S and T. Okay, so we should be able to look at sets here and then try to think about the different regions. And so here is a region, that region 7 there. Notice that it is things that are within T, also within S, but not R. Okay? And so we'll see some examples here where we're going to try to draw sets and try to figure out the number that are present in each set. Like, so if we knew that there were 5 elements here, and we knew the number of elements here, maybe we knew the total that was here in T, and then maybe we, like, so as I would start to like say numbers for these, there would get to be a point that you could fill in the pieces just by thinking of if I tell you in this region is so many, then you'll just make additional subtractions to kind of compensate for that. So we'll look at an example here of that. But really, we're just trying to show the different aspects of the sets and how they belong to other sets as well. We do need another notation here. So if S is any set, we'll denote the number of elements in set S by this notation N of S. And so pretty straightforward here. So again, S, so we're using braces again. There's 3 elements in the set, so the number of elements in set S is 3. So let's look at the statement here and see if we can convince ourselves that this is true. Okay. This is referred to as the inclusion-exclusion principle. So let S and T be sets. Then the number of elements in the union of S and T should be the number of elements in S, the number in T, and then subtract the number in their intersection. Remember, intersection would be both. Okay? So the number in the union should be the number in each minus the amount, the number in the intersection. And I hope you've already seen why that's true. If I think about the number in S, and this kind of goes to that first point, like if I would know the number of elements here, and I know the number of elements here, notice that we counted this region twice, thus the reason for the subtraction. So let's look at an example here. Give you a second to read that. And what I'd like you to do is start trying to draw a representation to figure out the answer to the question. So pause the video, take a minute, try to draw something out. Okay, so I hope you took that step. And so we'll try to kind of sketch here and then show the answer as well. So as we think about the 310 number here, so 310 had degrees of any sort. And so here I have S being the undergraduate degrees and T being the graduate degrees. So I'll zoom out and show that here again in a second. So when we think about this 310, so that means that in this group, there's 310 people. Now, think about like even if you were in this group that had both degrees, you had an undergraduate and graduate, like you wouldn't be double counted here, right? You would just be one of the 310 people. And so when we think about that, that's actually telling us that the union of the sets is 310. 238 had undergraduate degrees in business. So maybe I should have been more specific here. So that's the number S union T is 310. So the number in set S is 230. And then 184 had graduate degrees. And again, think about that, we are potentially double counting here. In fact, if we just look at the sum of those two pieces, if I just add these up, so 234 plus 184, there's, well, that's more than 310. And that should be a clue, so hopefully you've already realized the number that are in both sets. So again, I'm looking for those people that would have been double counted. We would double count them here, but they wouldn't have been here, so then that means our final answer would have been sum those other two up, minus 312, I'm sorry, 310, and the answer is 112. So inclusion, exclusion. Let's look at some other examples of Venn diagrams with some ideas of the complement. Okay, so thinking about three sets. So if we start with the same picture of three sets that are overlapping, and so if we say R, S, T, so where would R intersect S intersect T be in this diagram? Where would um, actually where would each of those be? So take a minute, sketch something, and then I'll show the answer here. It doesn't really matter the orientation of R, S, and T. So like you would know where this would start, right? So E, R, S, something like that. But we have three sets, so can you draw a Venn diagram representation of if they're interlocking like that first example, where would those intersections there be? So here is the first solution. R intersect S intersect T. That's the overlap of everything. So we're looking for what R and S has in common. So R and S has this in common. But we want to know where that has in common with T. So where does that overlap with the T set? That overlaps just in that shaded region. So the next one was the union of them all. So the union is all of this. Remember, the union wouldn't double count. You just see a different color here because each other. But we're just looking for taking a representation of each of them. Okay, so even in our set notation, I wouldn't list it twice. So just to be sure that we, so if I had a set that R was 3, 4, 5, and T were the numbers 1, 3, 4, 6, let's say, and then S was the numbers 2, 3, 5, and 6. When we think about the union of all of them, I'm looking for then really what they all have in common. I'm sorry, I'm looking for, I'll look at what they have in common, but I'm really only going to be writing, so I would write something like this. So 1 is present. Actually, let's start. -2 is present. 1 is present. I see a 1. I see a 3. I see 3 threes, but I'm not going to list it twice because there's nothing here about a set that says I need to include it more than once. Set's just, again, a collection of objects. So we have a 4, we have a 5, we have multiple 5s, don't care, we have multiple 6s, don't care. So I think I got them all there. We're looking for just one representation, even if they have something in common. So that is this entire grouping. So if we think about like certain regions, we could definitely start to, like we just talked about a region like this. So in this set, like what do they all have in common? Well, they definitely all have a 3, and I think that's it. So is there something that S and T have in common more than the number 3? And so if we look at S and T, so they share 3, but they also share 6. So 6 would be here. And then if we think about the set S, is there anything that S shares with R besides the number 3? Yes, they share the number 5. So the number 5 here. And then same thing with R and T. What do R and T share besides the number 3, which we've already decided? Well, they share the number 4. And then these remaining spaces should be any other numbers if they exist in the set. So like in T, there's number 1. We haven't, it's not shared. In the set R, there's nothing else. So this is really empty here. No elements there. And then S, there's the number 2. Okay. So last one, here's what you should have drawn. So S, where does that overlap? So we need to start thinking about what they then overlap with the complement of R. So the complement of R is like outside of R, okay? So there definitely is going to be overlap in um, this region, but um, we're also looking, we would actually have this region here, right? So that region that looks red is definitely outside of R, but it's also part of S. But now with this last piece, it also needs to be like we need to look for an intersection of outside of T. So as soon as I start looking outside of T, well, I'm not going to include that region, so that's not part of the solution. So I'm ending up here then with this shaded. Okay. So there's a little bit about those sets. Let's maybe look at another example. So can you take a minute, draw a Venn diagram, and try to decide how many students would fit into these groups of texting, listening to music, or doing both. I hope this is what you came up with. So here's our 15 that are texting. Here's our 11 listening music. There's the doing both. How many are how many are present in the lounge? There would be 18. 7 plus 3 plus 8. Last thing. So we're gonna look at, on the wrong slide, we're gonna look at something called De Morgan's laws. De Morgan's laws. So let S and T be sets. And so if I would think about the union of S and T and then take its complement, De Morgan's law says that's the same as the intersection if I would take the complement of each. And I'd like to think about that, just try to verify that thinking through a Venn diagram here. Okay. So I have an image here of S union T. So if I wanted the complement of that, that definitely would be thinking looking outside of where the subs are overlapping. And if I do that, you notice it would look like this diagram. Okay? So that's the complement of union of the two sets. So if I think about this right-hand side, it says if I would think about S and its complement, and think about where that overlaps with the complement of T, the picture should look just like that. Okay. So if I would think about the complement of S, so I'll go back here, I'm going to make that in blue. So the complement of S should be everything outside of S, which would be, roughly something like that. And then if I was going to do the complement of T, I should be looking for everything that is outside of T, which would be that. Now, the goal is we want the intersection, so I should be looking for where they overlap. Basically, where did I draw both colors? Well, do you see it's really what this image is? It's everything that's outside of the two. So De Morgan's law is a way um, to see a connection here between the complements and just something that will be equivalent. Sometimes it might be easier to make a rearrangement like that and do that, but this one I'll leave for you to kind of think about verifying for yourself of, of constructing those complements and showing they're the same. So again, this is just a bit of 7.2. I hope it's enough to um, let you get through the 7.2 homework, and so should be something posted for you to work on, and we'll pick up here when I'm back. See ya.